Okay? There's one more thing I want to talk about that talks about how to think about this stuff. Okay? Why does burning anything always release energy? If you ever think about it, we talked about we can have endothermic reactions. We had the example at the very beginning of class. You can have things that get cold. Why is it that when you ignite a carbon-containing substance, there's no such thing as you ignite a carbon-containing substance and it gets cold? It always releases heat. And that actually doesn't have to be true. Why is fire always hot? It's not why is fire hot in one case, but why is fire always hot? Why does stuff always combust? And it must have something to do with oxygen, because that's the key part of combustion. It's a key part of our atmosphere. But why does oxygen combine with carbon and always give you an exothermic reaction? That's the question that they ask right here. And it's really a question about oxygen. So one of the things that you can see is the answer has to do with the structure of oxygen. The double bond in O2 is much weaker than other double bonds or pairs of single bonds. And therefore, if you're making CO2 or even single bonds of H2O, these are actually stronger bonds than the weak double bond here. And I guess that's what the really weird thing is. You have a double bond here, you break it, and you make single bonds, and that gives you energy. That's not normal. Why is it that this always happens? Couldn't there be a case where you make H2O single bonds and actually combustion actually is endothermic rather than exothermic? Well, regardless of the fuel, we always see that fire is always hot. So they wanted to ask that question, why is fire always hot? And so they did calculations, but these are all calculations that are along the lines of what you've done and what you can do. So for example, you can burn carbon, you can burn coal, and you can react it with hydrogen, and you make methane. You can do the same reaction in the presence of oxygen, and you'll get CO2 and H2O. Okay, the only difference here is that you have the O2. Now look at the difference between these two things. The only difference is that you have O2 added in. All the molar amounts and everything else is the same. This gives you 10 times more energy, like 12 times more energy, because the delta H for this reaction is almost 1,000 compared to 75 for the no oxygen reaction. So this is the observation that we see. Oxygen always gives you an exothermic reaction, consuming this bond, breaking this bond. And if you take sugar, of course, you get this famous thing. This is you've actually had this in a homework problem. The delta H of this reaction is negative 2,800 kilojoules per mole. That's a ton of energy. And what you're doing is you're breaking these bonds, you're breaking this bond, and you're forming these bonds and that bond. And that's giving you this energy. The fact that there would be some reactions that do this is not unusual. The fact that every reaction does this, and there's never a reaction that goes the other way, is weird. And you can compare it directly. What would happen if you burned this, like this one, if you burned it without oxygen, with just hydrogen? It would still give you energy, but it would give you about 4 times less energy. And so they wanted to look at this, and here they have a typo. Here they have a real typo, okay? Actually, I'm going to, you don't even really need to read this. It's a typo in the equation, I'll tell you that. Can you find the typo? Yep, they did that. I think I've done that on the whiteboard myself, so I can't throw stones. But you can definitely do that. You know, you can definitely see that. So you had just copy edited a peer-reviewed paper. Congratulations. But what they've done is they've done heat of combustion is heat of reactants minus heat of products. You can do this with enthalpies, and it's what we've done. And so what they did is they did examples. Like for example, this is burning methane in oxygen, gives you this much energy. Combusting hydrogen in oxygen gives you just water. There's no carbon around. That gives you energy still. The only thing that's constant to all these is that they have oxygen involved. Let me lift this up a little bit. Okay. But the thing that they show here So they're showing both of these reactions in these terms. This is a really kind of complicated thing, but this is showing what goes on in your head when you think about the energy levels. Here's the energy level of reactants and the energy level of products. So in this case, you have CH4 and CH4 combusting. It starts off right here, so it has a heat of formation of at this level right here. And then when it combusts, it makes CO2 and 2H2O. So when it combusts, it makes 2 times 804 negative, and 2 times 927. So these bonds form, these bonds get broken, and the oxygen, this bond gets broken as well. And so the way you calculate this is you just do a chapter 1 type calculation. You take this kilojoules per mole times 4, this kilojoules per mole, but you always do the products minus reactants, and you end up with negative 890. The thing that they're showing you right here, notice how much higher the oxygen level is than all the other levels. And it's true for both of these reactions. They're showing 4 H's and H2O. The oxygen heat of formation, so the heat given off when the bond's formed, is a lot less than the heat of formation of anything else. That's why they say it is a weak bond. Even though it's a double bond, its heat of formation is really low. And so that means that you can break it apart and consume it. It doesn't take as much energy to break the bond, but when it bonds the other stuff, it forms really strong bonds. So it forms a weak bond to itself and strong bonds to everything else. This is directly related to some of the talk at chapter 3 or 4, I believe it is, in A World from Dust. The main thing is, this is exactly like your homework. Here's an example of, and I'll tell you what's cut off at the top because we don't have this fit. This is in general, if you take anything containing carbon, hydrogen, and oxygen. If you're breaking carbon-hydrogen bonds, you're breaking these blue bonds. If you're breaking OH bonds, you're breaking these. When you combust these, you break these bonds, and you form these bonds. Because oxygen is, again, high up here, it's a weak bond, even though it's a double bond. When you break it, it's not that hard to break it. When you form it, you get stuff that's down here. So that means that breaking oxygen is easy to do. When it forms, it gives off a lot of energy because it forms tight bonds. CO2 and HOH are very tight bonds. So the reason why everything burns is basically because OO is a weak bond. And it forms super strong bonds when it binds to C or H or even nitrogen or pretty much anything else. Therefore, when you're burning something, you're always breaking the oxygen bond, and it always gives you a little bonus. So actually, they wanted to say, okay, what's really important here is not exactly the structure or even the number of bonds that you're getting out. The big difference here is how much oxygen are you consuming. So if we're right that it all depends on the oxygen, we should be able to take data from pretty much any structure of C's and H's and N's and O's. We should be able to take data from any structure burning in oxygen, and we should be able to plot it out and say that the main thing that determines how much energy I'll get out is how much oxygen is consumed. Doesn't matter how many CH bonds I have, how many CC bonds, because they're all sort of down here in the same region. It's oxygen that's unusual and always consumed in large quantities. So they actually did this right here. I guess I'll show you, they actually calculated the heats of combustion. They used standard. I just did this to show you, there's one more thing that they had to do. Notice that with this, you're forming H2O liquid. And all of this is talking about forming bonds. It doesn't talk about forming the bonds, the intermolecular bonds. And remember we said you had to account for that. This is where they account for it. They say on top of the calculations just from the heats, we have to say that whenever we're forming water, that water condenses and that gives us energy as well. And we have to account for that as well. But you can calculate that. The enthalpy change of water from gas to liquid is negative 44 kilojoules per mole. So they basically say the heat of combustion, you can estimate the heat of combustion for anything that contains carbon, nitrogen, oxygen, really anything, and gives off water by taking these two terms, negative 417 times the number of moles of oxygen you're consuming, minus 44 times the number of moles of water liquid that you're producing. This is a much smaller number. This is like a 10% difference. You get 90% of what's going on just by accounting for the oxygen. This is the graph that they ended up making. And the main thing is that they took a bunch of different molecules and they took the data and they plotted the heat of combustion versus the number of moles of oxygen consumed, plus a little term for the water, number of moles of water made. And it forms a perfectly straight line. In other words, it doesn't matter what the bonds are or what the order is, what the structure is. It's all going to combine with oxygen. And the energy you get out, 90% of the energy you get out is proportional just to the amount of oxygen that's consumed. And if you account for the water is the next biggest factor. 10% is that. So this is why fire is always hot, because fire always consumes oxygen, and oxygen is the main thing that's going on. And you see immediately probably how that goes along with the message of the book, because it's all about the oxygen. So our conclusion is, what makes fire hot, and even how much heat is produced whenever you combust fuel. And what it depends on, again, is not the fuel, it depends on the oxygen. It forms stronger bonds in CO2 and H2O. And generally, our analysis indicates that it's not the organic fuel, but rather O2 that is energy rich. The presence of large quantities of O2 in the Earth's atmosphere, in spite of its high enthalpy, is explained by photosynthesis from H2O, a ubiquitous proton and electron source for plants. So if the plants, it's oxygen-based photosynthesis that gives us the ability to get all this energy out. And it's the difference between, 100% and 10% of the energy. It's a big difference. And that's why I think oxygen is important. All right, that's the data talk.